This is just a little bit of further explanation for the previous question about non-equilibrium. So you see in the book slide, there was perhaps a sentence at the top here which caused a small confusion. Rather than saying that non-equilibrium cooling leads to core destructure, they had written equilibrium cooling, right? So the main thing is rapid cooling delays solidification, right? This normal line, and this normal line is there, which is the homogeneous normal. But if we cool it quickly, then this line comes up, this is quicker than normal if the cooling rate is faster. If we allow it to cool very slowly, for example, let me give you an example. If I have put a metal in a furnace, the furnace is closed, it is totally airtight, it is closed, and I have heated it. Now I shut down the furnace. So I had heated it to 300 Celsius. I have shut down the furnace, but I am not opening any doors. So it is all closed, it is airtight, and the temperature goes down. Now the temperature goes down at a very, very slow rate. But I shut down the furnace and open the door. Now suddenly the temperature starts to go down very quickly. Or I shut down the furnace, open the door with forceps and thermal gloves and so on, take the metal outside and put it outside in open air. It starts cooling at an even faster rate. I take it outside, put on the table very carefully, and turn a fan on with the fan directly hitting the metal. Then it cools at an even faster rate. So I am telling you different practical versions of cooling. I can shut down the furnace without opening the door. It cools at a very slow rate. I shut down the furnace, open the doors. It cools at a faster rate. I shut down the furnace, take the metal outside. It cools at even faster rate. I put a fan on it, it cools even at fast, right? So there are different practical ways, and people who are metallurgists or materials engineers dealing with metals and alloys, they know how to do these things, right? So this line is a line of the faster things. So if faster things are there, then cores will be formed, and homogenization is there to eliminate the core structure, and the temperature of homogenization must be a certain something and so on. So this was there only as an explanation of what is non-homogeneous. Let us go to the next question. This is also from phase diagrams and so on, but this is a numerical problem. Consider the binary eutectic phase diagram shown in the figure. Make phase analyses of 80 weight % silver, 20 weight % copper alloy at a temperature of 900 and a temperature of 780 minus delta T. In the phase analysis, include phases present, chemical compositions of phases, mass fractions of phases, and sketches of the microstructure. So we have done this type of a question many times during the course. We have done lots of examples, we have explained them to a lot of detail, so it should be pretty easy. The only thing that we can generally change is that we are giving you a different composition and a different temperature and so on, right? But some students, when we look at the solutions, unfortunately, unhappily, it looks like some students, many of you have done it very nicely, some of you have done it 100% correct, some of you, unfortunately, right? Because I keep on reminding that when you come into the university, this is the best university in the country, and College of Engineering is a very high percentage tough college. So when you enter into the College of Engineering in this university, you are some of the top students in the country. So you are really very good, but it is maybe only because you do not give it enough time or practice or so on. So there is some effort lacking. So some students have done strange things. This 80 silver, 20 copper is one alloy. It is one alloy in which the percentage of silver is 80 and the percentage of copper is 20. One or two of you have taken it as two alloys. 80% alloy, they are solving, 20% alloy, they are solving. I have no idea what they are trying to do. I have no idea what they are trying to do. You see, if you say 80% silver, I am trying to explain it to you again as if we are in a lecture. 80% silver. What does it say? Weight percent silver. So silver goes from 0 to 100. So this point is the 80% silver. If you want to see weight percent copper, then copper is 0 here and 100 here. Weight percent copper goes the other way around, right? 0 here and 100 there. So if you want to go for weight percent copper, then from 0, this is 10, this is 20. So 20% copper is the same point, please. 80% silver, 20% copper, whether you measure in terms of silver, which is going from 0 to 100 here, so 80 is here, or copper, which is going from 0 to 100 there, for copper 20 is here. So whichever way you see, it is the same alloy, but one or two unfortunately were solving for 80% silver and 20% silver as 2. So this is very strange. Okay, and at any given temperature, give me the 4 answers, right? So I will solve it on the next pages and so on, but we can discuss the solution right here. So again, right, for you, if you have done it very well and you are 100% sure, then you just go ahead to the next slide. Otherwise, if you are a little doubtful or you want to do more practice, then just solve it again. Take a blank page, solve it again. And once you solve it, then look at the solution. Right, so 80%. This is 80% silver. You just draw a very big straight line, vertical line. This is how you solve it. And then you have two temperatures. You have 900 Celsius and 780 minus delta T. So at 900, this is rough. You should be very exact. At 900, make a horizontal line. At 780, you don't want to do any line because the exact perfect line is already here, right? So the horizontal line at 780 is already drawn, and this is the horizontal line there. So now all your answers are here except a small bit of calculation. So for first part, your initial alloy is 80% silver and initial temperature is 900 Celsius. This is the point which you have. This is the point. So now answer the 4 things here. What are the phases present? Only liquid phase. What is the composition of the phases? It is only liquid and the composition is the same as given 80% silver. What is the weight fraction or mass fraction? It is 100% liquid because there is nothing else. And what is the diagram sketch? There is a circle and everything inside the circle is liquid, right? So this is it. You answer the 4 questions at 80% silver. So I am recapping, right? Part A, at 80% silver, at 900 Celsius, draw the vertical line, draw the horizontal line, find where the point is, and then answer the 4 questions. What are the phases present? What are the compositions of the phases? What are the mass fractions of the phases? What is the sketch? Okay. And if you go to the other one now, part B, so the vertical line is still the same, but the horizontal line is this one. Horizontal line is this one, right? But just below it, so just below, right? So the point is here. This is your point. This is your point. But you are not above the line, you are just below the line. So if you are below the line, where does it cut? It cuts here. It cuts alpha at 7.9. Right? And if you are below the line, it cuts beta where? Cuts beta where? At 91.2. So the vertical line is this, the horizontal line is this, but try to think that on this horizontal line, you are just below this line. So where does it cut? This line, it cuts alpha at 7.9, it cuts beta at 91.2. So if you draw a line, horizontal line, then in the middle you have 80, on the right you have 91.2 representing beta, and on the left you have 7.9% for alpha. And if you have this horizontal line, the tie line, then you do the solution. So now the solution, this part we have discussed a lot. The sketch just says that this is 100% liquid, but phases only liquid, composition 88% silver, mass fraction 100% liquid. And just below you have, right, phases alpha and beta, right? Phases were alpha and beta. Composition alpha 7.9% silver, beta 91.2% silver. Mass fraction lever rule. Draw a horizontal line. This is a line in which W naught, the middle is 80% silver, left is alpha 7.9% silver, right is beta 91.2% silver. So from the lever rule, if you want to find mass fraction of alpha, remember, if this is the tie line, we have told you many times in the lever rule, for mass fraction of alpha, you go to the other side, you go to this side. And for the mass fraction of beta, you go to the other side. So this is important, right? So for mass fraction of alpha, you take this minus this, 91.2 minus 80 above, and below, of course, is 91.2 minus 7.9, the whole line. And for mass fraction of beta, this is opposite. Don't take this side, opposite side, 80 minus 7.9. And below, of course, the total, 91.2 minus 7.9. So you have the answers. The mass fraction of alpha is 13.44%. Mass fraction of beta is 86.55%. Now, if you sum them, it is 99.99%. So you are sure that you did right. And I have told you many times that please don't say mass fraction of alpha is this and mass fraction of beta is 1 minus this. Because if you have done it correctly, then 1 minus alpha will be okay, it is beta. But if you have done it wrongly, then your second answer will also be wrong. So please do calculate both of them by the lever rule and then sum them up and see that the sum is roughly 100 or not. And now, if you want to understand this was critical. This was critical. We were going on the right hand side, right? This was 80%. It was not on the left hand side. Left hand side, the liquidus starts alpha, then right, alpha plus liquid, then alpha plus beta. On the right, it starts beta plus liquid, then alpha plus beta. So the pro-eutectic is the beta here. It is not pro-eutectic alpha. This is very important that it is not on the left hand side of the diagram. This percentage of 80 weight percent original is on the right hand side. So when you go from here and cuts the liquidus, the first solids that form are beta solids, and beta plus liquid keeps on going until you get beta and alpha. So pro-eutectic beta is there, and then once you hit the eutectic line, all of that is converted into alpha plus beta, and that alpha and beta is eutectic alpha and eutectic beta. So these lumps are pro-eutectic beta, and all these dashed lines are eutectic alpha and eutectic beta together, right? So we had covered this very strongly in examples and so on, but as I said, I was very satisfied and very happy that many of you got it 100% right. Some of you got small errors here and there. So if you got small errors here and there, then this review session would hopefully make it very solid in your mind. And unfortunately for those, unhappily for those who did not give it enough preparation time and so on, they made a lot of mistakes and so forth. The sketch was not right, the calculations were wrong, the compositions were not there. But remember, I can ask you only that give phase analysis without giving any detail. But when I ask you give phase analysis, it means what are the phases? 1. What are the compositions of the phases? 2. What are the mass fractions of the phases? 3. What is the sketch? 4. Here I have explicitly written that do these 4 things. But in a future question, even if I just say do phase analysis, then you should do all these 4 things. Okay? Good.